Hi, welcome to another session of our KieLive series, where we intend to bring content about all the projects under the Key umbrella, which would mean, do you know, Mr. Alex? Of course you do. Could you list the projects under the Key umbrella for us?
We have under the Key umbrella, we have the rules, JBPM, OptaPlanner, and the new Cogito.
Oh, yes. So all those 4 projects, we always bring news about it, deep dive content, and also content for getting started. So for today, we will talk about OptaPlanner, and we are going to talk about a specific feature, which is called shadow variables, which is actually, the reason why we're bringing this content is actually because people from community asked for it. So on the last session with Geoffrey, people were asking, could you please talk a little bit more about shadow variables, right, Porcelli?
Yes, exactly. That was the live feedback during the session. People, can you clarify this and that? And was and Geoffrey during the live. Well, that may be a theme for just one particular deep dive session. And here we are. We have Geoffrey to help us and understand the shadow variables. And to be honest, this is a thing that I don't know much, and I'm really eager to learn.
Especially because it is used on use cases like the vehicle routing problem and also the task assignment and much others. If you go to the OptaPlanner documentation, for example, you will see at least 6 examples of use cases with the code sample using the shadow variables feature that we are going to learn today. Shadow variables can be of different types, and Geoffrey is going to mention all of those. What is it? When to use it? And why it's important to use it. And yes, send us your hi, send us your love on the chat. You know, this is a live session, and the special thing about being here right now is that you can actually interact with others on the chat. You can interact with us, and especially with our experts on the matter. So feel free to send whichever comments or questions you have, or even topic suggestions. Okay? What do you think about that, Porcelli?
Yeah, that's great. And without more delays, let's bring in Geoffrey.
Hey guys.
Welcome, Geoffrey. It's good to have you here in the second session. That's awesome.
Good to be here, especially in this new year.
Yeah.
2021, our first session on OptaPlanner. Is it going to be a deep dive for people who already use OptaPlanner, Geoffrey?
Yes, actually. Yes, this is definitely going to be a deep dive. I'll try to make it start easy. But it's going to be a deep dive, and it's very useful in some cases. And I've seen people struggle with shadow variables, so this should definitely help to make it clear what exactly they do and how to use them.
And I'm just curious. I've heard that you have published a Q&A session with InfoQ about OptaPlanner 8. Today, are you going to use OptaPlanner 8 to tell us about the things you're going to... Actually, are you going to bring any demos?
Yes, of course. I'll show a bit of vehicle routing and task assignment, of course, and explain where exactly we use the shadow variables there. And I'll do some live coding too on actually add a shadow variable. So,
I think you're getting addicted to live coding.
Yes, it's a lot of fun.
Yeah, it's a lot of fun.
It doesn't break. Yes, exactly. Let's hope it works, and if it doesn't, this will be spectacular too. It will be entertaining.
Awesome. Porcelli, is there anything else you want to bring before Mr. Desmet starts with his presentation?
I don't think so, but be sure that I will ask questions during the session.
As usual. We love to interrupt the speakers. Geoffrey, I will share your screen right now, and feel free to start your presentation. Thanks for being here. And hi to everyone in the chat. Statis, Paulo, David, and Katie, and Donato, Nitin, everyone. Yeah. Nice. Happy New Year. Let's go for it.
Thanks, guys. So OptaPlanner, I'll talk about the shadow variables for vehicle routing problem and task assignment. So what is a shadow variable? Well, if we have a genuine variable in OptaPlanner, let's say the integer a, where we can choose any value between 1 and 10, then we might also have a shadow variable, which is an integer b, where it is the value of a plus 100. So for those of you who know what variable shadowing is in Java and stuff like that, this is unrelated. A shadow variable is something specific, a specific concept in OptaPlanner, and it allows you to say that one of the variables that does change during planning is actually dependent on another variable, and so it doesn't have any freedom of itself. We cannot simply choose any b we want. It must be the value that a is assigned to plus 100. So let me give you some examples of that. So for example, if a is 1, then b is 101. If a is 2, then b is 102, and if b is 7, if a is 7, then b is 107. Not really a big surprise, right? So if you think about it, if you put your hand in front of a light and it just casts a shadow, the shadow doesn't get to choose its form. It is actually dependent on how you change your hand. If you make it like a dog or a bird, then the shadow will look like a dog or a bird, right? So the shadow is determined by the object that it is shadowing, right? By its source. So in this case, the source is A, right? So why are shadow variables useful? Because you might think, okay, in this particular case, if I have an int A, and this is a genuine variable, right? And I have a getter for that, get A, which returns A. You might think, well, I can simply add a get B, which returns A plus 100, and that would be exactly what you need. And this is not a shadow variable, right? It's a non-simple getter. A shadow variable is more complex, actually. In a shadow variable, what we say is we actually have an int b2, and we tell OptaPlanner we tell OptaPlanner every time you change A, I want you to also change B, and this is the way you change B. So for this particular case, A plus 100, I wouldn't actually use a shadow variable. I would just simply return, just add a simple, a non-simple getter, right? A smart getter, right? But there are cases where shadow variables are actually very useful, and just this approach where doing some extra code and some extra logic in this get B method isn't useful. So just to illustrate that, let me talk in the last session about domain modeling. We ended with talking about assigning time to planning entities. And for those of you who didn't see that, let me just refresh you on how that goes. When we need to decide which time certain things happens, there are a couple of different patterns on how you can do that. One of them is the time slot pattern. And in the time slot pattern, for example, here we were assigning lessons to time slots, and these time slots start at a particular time, 8 o'clock. Now, in this case, you don't need a shadow variable, because if you want to know what time math starts, you just do math, get time slot, get start time. If you want to know when Spanish starts, you do Spanish, get time slot, gives you time slot 2. You ask the time slot, when do you start? And it says 10:15, right? So in this case, again, in this pattern, it's very unlikely that you use shadow variables. There's another pattern called the time grain pattern. And in this one, we actually have the ability for these things that we're planning, and in this case, it's meetings, to actually start at any time. Well, not just at any time. They can start at 8 or 8:15 or 8:30 or 8:45. We call this time grains. There's a certain granularity, in this case, 15 minutes. And what we do is we say, okay, we assign these lessons to a starting time grain. And then, for example, they might be 4 time grains long, right? Like in this case, the sales meeting. Now, what's the advantage over the time slot pattern is that now we can have the sales meetings they can be of different lengths. For example, the sales meeting is 4 time grains. The board of directors is a lot more, actually 8 time grains, right? The stand-up meeting is only 15 minutes, 1 time grain. So unlike in the time slot pattern, where we basically have to keep all of the time slots in the same length, all of the lessons in the same length, especially when they can be interjected, assigned to the same time slot. In the time grain pattern, we don't have that limitation, and so this is actually a step up from the time slot pattern. But it's also more complex. It's actually it increases the search space a lot, and it's difficult to get good results with the time grain pattern quickly. However, it does allow for example, planning breaks in between, gaps between two meetings here, as you can see, of 15 minutes, and actually have OptaPlanner decide how long that gap will be. It could move this event coordination thing 2 or 3 time grains to the right, so make it 30 minutes later, and then there's a 45-minute break in between. Again, in this case, do you need shadow variables? And the answer is no, because if you want to know what time the architect's meeting starts, well, you just look at, okay, it's time grain 1. Time grain 1 is actually the 8:15 until 8:30, so it starts at 8:15. When does it end? Well, it starts at 8:15. It's apparently 6 time grains long, so that's very simple. It ends at 9:45. You can do a very simple calculation saying, okay, my time grain, the starting time plus 6 times 15 minutes, and then you know when it ends. Again, not really need to have shadow variables in there. But one pattern that is used a lot, the pattern you want to use for vehicle routing problem, for task assignment, and many other use cases too with OptaPlanner, is the change through time pattern. And in this case, OptaPlanner is not assigning these entities, these things it needs to schedule. In this case, it's a task to do the French taxes, the Dutch taxes, the Belgian taxes, the Spanish taxes, and the German taxes. In this case, it's not assigning these to a particular time, but it's actually assigning these into an order. For example, Anne will first do the purple job and then the yellow job. So the French taxes and then the Spanish taxes. Now, as a side effect of that, we know what time Anne starts. Anne starts at 8 o'clock. Bet starts also at 8 o'clock. So we know when the French taxes will start and when they will end. They will start at 8 o'clock. They take, apparently it's not really clear here, but about maybe 75 minutes or something like that. So it ends around 9:15. Right. You can see here the green one, NL taxes, takes 52 minutes, so it ends at 8:52. Now, when does the Belgium taxes, the blue one, begins? Well, when the task before that ends, of course. So that basically means that we know BAT starts at 8 o'clock. We know that the previous tasks took her up to 8:52. So we know that the Belgium taxes, the blue element here, starts at 8:52. And so this is where you might say, okay, I have a lot of constraints, and these constraints need to know when this task starts and when this task finishes, right? One of those constraints could be that these tasks have a due time. They need to be finished before 5 o'clock in the evening, because this is a high priority type. And our task might need to be finished before noon, right? And you want to be able to check those hard constraints. So you need to know when these tasks will be done, or estimated to be done at the very least. These are all estimations, of course. And in that case, you need to know the start and end time of these tasks. And as I just said, you can calculate it, but if you have somebody who has hundreds of tasks, or even just 20, it can be quite expensive to actually figure out the starting time, because you need to go through the entire chain all the way to the beginning and then say, okay, this is the first time, task starts at 8 o'clock, and then count all of those durations, take a sum of all of those durations. And it's better in many cases to just have the starting time and the finish time on the actual task. And that's when you need a shadow variable, because the shadow variables will allow you to say, okay, I have a shadow variable, which is the start time. And then you can just say, if you want to check if it will start, if it starts sometime, you can just use that value directly. You don't need to go iterate through the entire loop of tasks. And this will actually speed up your score calculation in many cases too. So these are, in this kind of cases, shadow variables is a good idea. In the cases of, in the first two patterns, they are actually probably not such a good idea. So we have a number of built-in shadow variables. And like I've said before, the shadow variable is determined by the genuine variable. So if the genuine variable changes, the shadow variable changes too. So one built-in we have is what we call the inverse relationship variable, and it allows you to have bidirectional variables. So let me explain. We have a genuine planning variable, a process which we're assigning to a computer. This is from the cloud balancing example. So we're assigning a process to a computer. This has a planning variable called computer. What we can actually do, and you won't find this in the stock example that we gave you, of course, but what you can do is you can say, on the computer, I am going to add a list of the processes, a process list. And if you annotate that with inverse relation shadow variable, you're basically saying this is the inverse relationship of the computer variable. And then that means that when a process is assigned to a computer, that the computer's process list will contain that process. right? So you basically have a bidirectional relationship at that point in time. For those of you who are familiar with Hibernate and JPA, this probably rings a bell. The mapped by property. It's the same principle. Basically means that you have you can now go from a process to computer, and you can go from a computer to all of its processes. And this can be quite useful in your constraints. This can be useful in your domain if you're showing it in the UI and so forth, but it does come at a cost. And so for the cloud balancing case, I'm a bit skeptical on always particularly adding that just for your UI, but it is possible. Right. So when the genuine variable changes, the inverse relationship variable changes accordingly. For cases with vehicle routing, with anything with a chained variable, it's a little bit special because from a computer to a process, we have a too-many relationship because multiple processes can be assigned to the same computer. But when you're dealing with the vehicle routing case, anything with chained variables, for those of you who are familiar with that, we actually know that a chained variable always has that the other size is also a 2-1 relationship. So we actually know this is a 1-to-1 relationship and not a many-to-1 relationship. So the inverse relationship variable will actually not have a collection or a list or a set, but will actually have directly the customer value. It's a 1 relationship, right? So we actually know that and we detect it in OptaPlanner. So that's a bidirectional variable, but let me maybe show you in code, and then you're going to start seeing on how this works, right? So what I'm going to do is I'm going to work with the school timetabling example where we're assigning, for those of you who remember, we're assigning lessons to time slots and to rooms for those of you who've seen this case already. And what I'm going to do, and this is how the model looks like. We have time slots, we have rooms, we have lessons. The lessons are being assigned to a time slot and to a room. They have a certain subject, teacher, and student, of course. We have a number of constraints. For example, no 2 lessons in the same room at the same time. And what I'm going to do is I'm going to add a shadow variable, an inverse relationship variable, so a built-in one, an inverse relationship that actually points from the room towards the lesson. So I'm going to basically give the room a lesson list, nothing more and nothing less. Let's see how that works. Let me try to do that right now. So I've started up the school timetabling example with Quarkus. I'm going to just remove in the demo data generator. I am not going to assign one of the lessons yet. Let me just show you what that gives you. If I go here to localhost, here we go. Now we have the demo generator does generate all of the lessons, but it doesn't assign anything yet. And what I'm now going to do, so if we solve this, what do we get? We get a solution, and all of the lessons are assigned. There's a number of constraints in there. But if you look closely, what you'll see is that the number of lessons per room can vary greatly. For example, in this case, the middle room has 5 math lessons, while the left room has 5, 6, 7 lessons, and the room C also has, I guess, something like that, also has 8 lessons. So what we might want to do instead is we want to make sure that the rooms are equally used, so it's easier to, for example, clean them or do other improvements there. So what we want to add is we want to add a constraint that actually says I want to load balance the rooms across the lessons across the rooms. I want to have each room have the same number of lessons across the schedule. So before we do that, what I'm going to do is I'm going to go into the and I'm not in presentation mode, so let me do that. And let me add the exit full screen. Yes. So what I'm going to do is I'm going to switch to the I'm going in the domain. I'm actually going to in the room. I am going to add a list of lessons, right? So now each of my rooms will actually have a lesson list, and I'm going to just for now give it make it an array list and be done with it. Okay, so here we go, import class. Now, of course, these things are going into the database, and we're using JPA for that. And you can see that IntelliJ already helps us here, saying that there's a problem there. So what I'm going to do is I'm going to just fix this. This is not that.
Fix this. The next thing you're going to do is let me know if this demo will be available on GitHub.
I'm happy to. I can give the send. Yeah, I can make it. The demo is already available on GitHub as is, of course. The changes that I'm making is not. You can follow them here, and I'm happy to push those changes too into a separate repo somewhere. That's a good idea. Yeah.
Deal.
Thank you.
Thank you.
Thanks. So what I'm going to do here is this is a many-to-one relation. No, a one-to-many relationship. And I'm going to say in JPA that this is actually mapped by the room on the other side. So if we go to lesson, the lesson is assigned to a room. This has a many-to-one relationship. For those of you familiar with JPA, and on the other side we have the one-to-many is mapped by room. So this is a bidirectional relationship in Hibernate JPA. So what we did in OptaPlanner, we basically stole that concept, as you'll see in a minute, when we add the inverse relationship variable, right? Where we say, okay, we have something, and the real, the main is on the other side, and this is just the follower, right? What I am going to do, because this is JPA, I am going to make sure I'm going to fetch it eagerly. You probably shouldn't do that in production, but for easiness sake, I'm going to do that.
I cannot believe you're doing that, Mr. Desmet. I'm just kidding.
Yeah, it just makes it easier right now to demo this. I didn't want to completely remove the database to make this approach work, but this worked quite nicely. So okay, so I've added the lesson room. So what I'm now going to add is in here, I'll just put it here. I'll add a get lesson count. Okay, so here I'm just going to add the return the lesson list dot size. Okay, so that's the lesson. So basically, every lesson that is assigned to this room should end up in this lesson list, and we're going to return the count. And then, of course, I'd like to actually show that count. So in JavaScript, for those of you who, well, I won't talk about my fondness of JavaScript, but let me just add the room lesson count in here. So that's the number of lessons assigned to this room, and we're going to put that between braces. And if we now actually go back here, we're probably going to see it crash, but it doesn't. That's good. Here we have lessons. You can see 0 rooms, 0 lessons assigned, right? Now, if we solve this, what we now see is, let me stop it. We have 9 lessons assigned to room A. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. 6 to room B and 5 to room C. So this actually does work. Now, that's because OptaPlanner, when in the school timetabling example, when it saves a lesson, it saves which rooms it's assigned to, and that's only it, and goes to the database. And by the time that the UI actually fetches all of those lessons, it also fetches all the rooms from the database. It does go through the Quarkus middleware, but it doesn't go through OptaPlanner anymore. And so this comes up nicely. The number of the lessons are actually in there. Now, let's try adding a constraint. So let's try adding a constraint. So if we go to the constraint provider, because we can clearly see this is not load balanced, right? We now have too few lessons in room B, and in room C definitely, and we have too many lessons in room A. And even if we solve it for a while longer, you will see that it might by accident be a little bit more load balanced. And in fact, it got worse. It just got worse. But because there's no constraint to actually push OptaPlanner into doing this. So one thing we can do here is we can say, okay, in the constraint provider, we can say, okay, I want to do a room count constraint, right? And let's add that. Here we go. And so we can say, okay, there's a couple of ways we can write this. One of the ways, which would probably be the right way, is that we say we just do a from on the lessons, like in SQL select from. We're going to do a group by all of the lessons. We're going to group all of the lessons by room, and then we're going to say constraint collectors dot count, and then we're going to penalize that. This is the room count we're going to say this is a soft constraint, but I'm going to make sure it's a pretty big soft constraint. So I'm going to give it a weight of 1,000. Why? Because we have these other constraints playing along, and I want to make sure that this one outweighs them, so that we really see those low load balancing of those rooms. This is actually more like load balancing of rooms, right? But I'll just do the room count for now. This is all soft, right? It's a soft constraint. And I'm also specifically going to look at what is that count? I'm going to use that in that penalize thing, because now every time every room that is used will now get this penalization of 1,000. But what I actually want to penalize is the number of the room count, right, per room. So what we want to do is we want to say, okay, given the room and a lesson count there, what I want to do is I want to return something. Now I could just return the count, but turns out that if you have 20 lessons and you assign them to 30 rooms, then you will always have the exact same number of, the sum of the number of those lessons, of that counts of lessons will always be, what did I say, 20 lessons will always be 20, right? Because that doesn't change. What you actually want to do is, if you look at the problem here, you want to really penalize this 9 and really not penalize this 4, right? Because you really want to, or maybe you do, but you want to penalize the outliers. So you could start calculating the average of the rooms, but there's a better trick. And the better trick is you basically square the counts. So what happens is that the 9 really becomes a very heavy penalty, and OptaPlanner will do everything to bring that down to 8. And same for the 7. If it can bring it down to 6, it will do that. And by bringing them down, he will definitely not push it to even higher numbers. He will push it to the rooms which are less full, right? And so he'll push it towards those 4s, and then we'll get to 5. And let's see what happens if we do that. Oh, we have an error. What is the error? Oh, live coding is fun. Missing return statement. Oh yes, of course. Here we go, and that should be better. Okay, so we solve, and what we see now is we actually see what we want to see. 7, 7, 6, right? You've probably noticed at this point in time, I haven't used any shadow variables. I haven't used any shadow variables yet. I haven't used the inverse relationship variable yet. That's because I started from the lesson, and I did the room count. So I can actually implement this differently. I can also say I'm going to start from the room. So let me comment this one out, and let me say instead I want to return a constraint factory from room class, and I want to use the I don't want to group by it anymore. I'll just filter it that the room get lesson count is higher than 1, and I'll just say, okay, I want to penalize that, right? And penalize is pretty much the same as before. We do room count. This time we just have the room, not the, and we just do room get lesson count, and we square that number, right? So basically now what we've done is, instead of going through the lesson and grouping those, we've actually relied on the room count which is in in this particular getter, right? We've relied on this, which of course relies on the lesson list, but OptaPlanner doesn't know when it changes a lesson and it assigns it to a different room, that it should be updating this lesson list right now. There's no information for it. It doesn't know that this room.lesson list field is connected to the lesson.room field, that they are bidirectional. They should be in sync. They should be the same thing. And of course, when we run our code right now and we solve this, we can actually see that in the room list above. You can see the 965 again, right? You can see that, in fact, it's not doing what it's supposed to be doing. And if it does, it's just by accident. So let's fix that. So how do we fix this? And this is where we're going to introduce our first shadow variable. Well, we're going to add on the lesson list here, we're going to add our built-in shadow variable called the inverse relationship variable. And this needs a little bit of information. So it actually needs one thing. It's the source variable name. So what does that what does that do? Well, it knows from looking at this that this is a list of lessons. So it knows that it's actually the other side of something of lesson, but it doesn't know on lesson what it is. Is it the other side of time slot or teacher or room? Now you could argue room is the only thing that fits type-wise, but it doesn't want life to guess, right? So you might have actually two rooms here, a published room and a non-published room, and things like that. So we don't want to guess. So we need to tell them it's the room side. Notice how this mapped by in JPA and this source variable in OptaPlanner, they're basically giving you, it's the same thing. We need to tell them what is the other side. And of course, these are in sync. Now you could argue, why doesn't OptaPlanner look at the JPA annotations, but we don't want to make OptaPlanner core dependent on JPA, right? We do have JPA integration. We might want to do it there, but right now we don't do this yet. Okay, so let's see what happens now. So we swap again, and we run again, and now it actually, let's see if it starts working. Let's see if I forgot something. Looks fine. And it should be bringing them together. You can see the numbers here. And why isn't it? It does show up in the score, but it's not really solving them right. So let's take a look at what I did wrong versus my implementation. Oh yes, of course, the most important thing, the mistake that everybody makes, and guess what? I've run into it myself, the pitfall. OptaPlanner doesn't know that it needs to look into the room class to actually detect this inverse relationship variable annotation. So this is the pitfall that everybody runs into. So please, if you remember one thing from this lesson, from this video.
I am sure this is the thing that no one is going to forget about this section.
That's good, that's good. I've seen it so many times on Stack Overflow and so forth. This room needs to be, this room is now something that OptaPlanner needs to manage, right? And so it needs to, this is an add entity thing from JPA, so it ignores that. So we need to add an add planning entity here for room. And in fact, but this is Quarkus, right? So in Quarkus and Spring Boot, just adding the annotation here is enough. But if you actually use OptaPlanner in embedded mode, you also have to go to your solver config. Let me show the cloud balancing solver config. You need to also add here an entity class for that room. And luckily, that is not needed in this case. So if I just add a planning entity here, now don't forget, don't make the same mistake I did, which almost cost me my live demo. You will see that now it actually does do it correctly. So this room is what we call a shadow entity. Why? It only has shadow variables. It's not really a real planning entity. It doesn't have genuine planning entities, but if you look at it from a number of things, like for example, when you want to remember a best solution and the working solution changes, you need to, OptaPlanner internally has something called a planning clone. It will actually also do a planning clone, not just for the lessons, but also for the rooms now. So for many reasons, it's a planning entity, but it's really a shadow planning entity, right? It only has shadow variables, but we still need to register it. Okay. So let's go back to the presentation. If there's any questions, don't hesitate to ask or to interrupt. We have a number of built-in shadow variables. So this is inverse relationship is for bidirectional variables. We have the anchor shadow variables. For those of you who are familiar with chain variables, this allows you to, for example, to know for a particular element in the chain, what is the anchor, what is the start of that chain. So for example, for a customer or a visitor in the vehicle routing problem, it would tell you what the vehicle is. For a task, it will tell you what the employee is. Very useful. You've probably seen those in the examples. We're working on more. One of them, for example, is to know the index in the chain if you have a chain model. Although we're working on far more interesting improvements around chain variables to begin with. Now, I was going to do also a demo for custom shadow variable, but let me just go through show you a bit of that code. Let me just make it a bit quicker for the interest of time. So what I'm going to do is I'm going to revert this, roll back this. Here we go. Sounds good. And I'm going to switch for a moment from no, I'm going to open my tool window on my shelf window, which is in Git here, shelf, and I'm going to just restore this state, and I'll go through this code here. Here we go, in the interest of time. So what do I have? I have, I've made the same changes in GS. I've shown the room lesson count, but I've made the same changes in the demo generator that I've not initialized and assigned anything anymore. But in the room, instead of actually having a lesson list, I've now added a lesson count. So as you can see, I've said, okay, I want to have a room. The room is, again, a planning entity because it has something that changes during planning, even though it's a shadow variable. But this time it's a lesson count. And so it's not a lesson list. And what we will see in the constraint provider, that my room count simply says, okay, your room, get your lesson count again. So it's the same constraint as I've shown just a second ago. The only difference is that this getter, this get lesson count, is no longer an actual, doesn't say lesson list.size, but actually brings back the lesson count. And you might also see I have also made sure that when OptaPlanner saves the solution in the database, it also stores this lesson counts correctly with the room. So that's in the times table resource, but I'll skip that. Now, how does this custom shadow variable work? So this is the annotation. It's no longer inverse relationship variable, but it's actually custom shadow variable, which basically means we can do whatever we want in there. And it has two things. First of all, the class that's going to implement the logic. That's going to say B is equal to A plus 100, right? And in this particular case, the lesson count is basically means every time a room gets added to a lesson gets added to a room or gets removed from a room, we're going to make sure we update the lesson count of that room. And that's the logic in there. And I'll show you that in a minute. But what's also important is the sources. This will tell OptaPlanner what the shadow variable depends on. So shadow variables always depend on genuine variable. And so OptaPlanner needs to know when it changes one of the genuine variables, which shadow variables might be affected. Why is that? It's because OptaPlanner uses incremental score calculation internally. This is a huge benefit when to be able to get good results quickly and to scale out incremental score calculation. And it's based on deltas internally. I won't go into those details today. Maybe another KIE Live session for that. But the interesting about that is that OptaPlanner needs to know when a genuine shadow variable changes, which shadow variables might change, and it will send an event to just make the changes on those rooms that might be affected. So when, for example, we add a lesson of math to room C, OptaPlanner knows it doesn't need to go through every one of the rooms and go through all of the lessons to make sure that the lesson count is up to date. It just needs to check, okay, this math lesson is assigned to room C now, so we need to increment the room count for room C. Just the delta, just to change in that, right? So, and that's extremely more scalable, and so this is a must-have if you want to scale. And so that's why we have this sources thing, which basically says, okay, this shadow variable is dependent on this lessons class, and more particularly lesson.get room, right, or set room. As you can see, this is a collection, an array, so you can actually add multiple things. You can say I have my lesson count is depending on multiple variables inside lessons, or even otherwise. You can even have shadow variables that are dependent on other shadow variables, which is very useful, which we do all the time. So for example, when you have an inverse relationship variable, you might say on that lesson list, I have another shadow variable that's dependent on that, and you can do that. And so you can mix and match those as you see, please.
Geoffrey, before we go deeper on probably I want to look at the variable listener code and some things, but we have a question that may not be, I'm not sure if you touch these again. So just to clarify and take the moment for that, why is that Solver's XML configuration needs the entity class element of the shadow variable? class explicitly specified. You briefly mentioned, but I think it was not exactly clear the reason. Could you expand more on that?
Yes. So if you're using the Quarkus extension or the Spring Boot extension, it doesn't need that. In fact, you don't need a solver config at all over there. If you do have one to power tweak OptaPlanner, you don't need to mention the entity classes and so forth, because what Quarkus will do is at build time scan your class path and actually automatically pick up these things with planning entity annotation. And Spring Boot will do the same time at bootstrap time during runtime. Now, if you use OptaPlanner embedded, however, we don't scan the class path. We did that before in the 7th series if you turned it on, but it is unreliable and it caused so much headaches and so much pains. We stopped supporting that in the embedded mode. And so the best thing to do, and we always support it, just explicitly mentioning them in the solver config. So it's a very good question though. So if, for example, in the cloud balancing solver config, if you say, okay, I want to add something on the cloud computer, you would need to add this one here, because this one, the cloud balancing example, uses the swing examples, and this one is actually using the embedded mode. As you saw with the lesson example that I'm using right now, we don't need to worry about that at all because Quarkus just picks it up.
Great, thank you. I think it was very clarifying. Thank you.
And scanning the class path, by the way, is expensive. So yeah, it's really nice that Quarkus does this at build time. That means that you don't suffer any performance or startup time at runtime. It's a huge win. Okay. Now let's go into the lesson count variable, listener. Here's where it gets a little bit hairy. Why? Because, as I said before, OptaPlanner really builds on doing everything with deltas, with incremental score calculation. So you, instead of saying, okay, so you actually get all of the events, and anytime a lesson is going to be, a new lesson is added, or before it's added, after it's added, when a lesson is changing to a new room, the original room might actually be null, or the new room might actually be null, but before and after that happens, and also when a lesson might be removed. Now in practice, there's very few use cases and very few users where we actually create and remove lessons during solving. So these two, the before and after removed, and before and after added, don't really matter much. I'm just going to focus on these two, on the before variable change and after variable changed. And so what do? They say, okay, anytime a lesson is assigned, before it's assigned to a new room, I need to make sure that whatever room it used to be assigned to now decreases its lesson count. So basically it says, give me the old room, the room before, so for example, the lesson math was assigned to room A. So give me room A. If, of course, it wasn't assigned to anything at all, we don't need to decrease that. But if it was assigned to something, if the room is different from null, we need to set the lesson count to the current lesson count -1. So we need to go to room A and say, okay, your lesson count is now 1. We need to decrement that. Now, OptaPlanner needs to know that that has changed, because that might actually affect its constraints calculations for score calculation. And of course, it wants to do that incrementally again to scale. So that's why you need to call this before and after variable changed of that lesson count. You need to actually signal OptaPlanner through the score director that this thing has changed, which allows OptaPlanner to figure out all of your constraints, which might depend on this lesson count, to make sure that those gets recalculated incrementally. So without recalculating the entire score from scratch for the entire solution, which is often 500 or 1,000 times faster if you have 1,000 or 2,000 lessons to assign. So it's really a big lesson, really big scalability gain. But these are the downsides. You actually need to tell before and after. Again, shadow variables are not for, it's a very powerful thing in OptaPlanner, but it's also not for your first time usage in OptaPlanner. We're trying to make it easier by giving you more shadow variables out of the box. For example, one of the things we might be thinking of right now is adding one for the arrival time, which I'll talk about in a minute. But anyway, so we also have the after variable change. So once the lesson is assigned to the new room, this is the new room, we need to check, okay, for this new room, we need to increase the lesson count because now there's one more. So what happens if a lesson is assigned to the same room it was already assigned to? Well, then we decrement it and increment it again. So basically the room count stays the same, right? So this code is fine. And you'll see that this code for the removal and when an entity gets added is pretty much the same thing. We increment the lesson count if we add one, and we decrement the lesson count if we remove one. So that's pretty much the logic behind it. And of course, if we run this, this again works. So let's solve this. And it does the same thing, but now the room doesn't have a lesson list, but actually has the lesson count, and that's done through a custom shadow variable, right? And so the big trick to remember here is on the room, we have the custom variable annotation, right? This is not a built-in thing. Now notice we could do whatever we want in there. We could, for example, instead of doing the lesson count, we could say, I'm going to count a distinct number of lessons based on subject or on teacher, right? How many different teachers do we have in the same room? And that might be useful for constraints because you might not want to have too many different teachers in the same room because teachers like to own or co-own a room, right? And so you might want to use it. Again, you could do that through your constraints, but in some cases a shadow variable might be useful. Okay, let's continue. So don't overuse shadow variables. In fact, the cases that I've shown so far are really not good cases except for the arrival time, which I showed in the beginning. So because shadow variables are denormalization. For example, the lesson count, that's information duplication because you know each lesson knows in which rooms it's assigned to, so you can actually count that up. Shadow variables work incrementally. Be wary of shadow variable corruption. It's not score corruption, it's shadow variable corruption. It's a different thing, but it feels very similar and it's a very similar danger. So again, shadow variables are really a power user feature. All of the built-in ones will not give you shadow variable corruption. So that's our goal, to give you more built-in ones. So basically, all of this complexity goes away for you, and you can still use those powerful things. Shadow variables, in this particular case, room.lesson count is probably not worth it. So in the vehicle routing problem, for those of you who are not familiar with it, let me just show you a quick demo. Where can I run? Here we go. We need to assign. So let me do that here. We need to assign vehicles to a number of visits where they need to pick up things. And this is where shadow variables are extremely useful. So over here, we have a number of locations where we want to pick up something. We even have time windows for this. So for example, at this location, we need to arrive between 12 and 1, here between 1 and 2, here between 2 and 3. And now when we solve this, and this is of course using a shadow variable, OptaPlanner will figure out the best route and the best order to visit these locations. You can also see it arrives here at 12 o'clock, here at around 1 o'clock, here around 2 o'clock. So always within the time window, except over here. Here it arrives too early. It actually pays the cost of having to wait there until it opens, and then it continues. So what is a time window? A time window means you have to be at this particular place between a particular ready time and a particular due time. So between between 9 and 12, you have to be at my location to install cable or something, a technician, right? If a technician needs to do that. Now, to be able to know if we are there at the right time, if we're not too late, we need to know the arrival time, right? So when we look at this in the vehicle routing problem with time windows, the input has a ready time. We need to be there after. We know we can only start to work at that time if we're there. A due time, we need to have the work done before that time. Let's say 9 o'clock till 12 o'clock. We have our service time. It takes 10 minutes to do the job. And then we have a number of things that change during planning. But remember, the only thing that OptaPlanner decides is the order of the visits and to which vehicle it's assigned to. So what we have is we have an arrival time. And this is the previous departure time plus the travel time. And you probably wonder what's the departure time. Well, let me first define the start time. The start time is the ready. This is the max of the ready time and the arrival time. So when I arrive too early, then we need to wait until the ready time. When I arrive after the ready time, then the start time is the arrival time, right? And then we have the departure time, which is basically the start time plus the service time. So we know the vehicle starts at 8 o'clock. That's the first previous departure time. So we know that it takes 10 minutes to go to the first location. So the arrival time is 8:10, and then we know that the ready time is 8 o'clock, so we cannot immediately start work there at 8:10. The service time is, let's say, 10 minutes. So at 8:20 we're done. We depart. That's the departure time. We go to the next location, and the next location's arrival time is basically 8:20 plus the travel time to that new location. And so forward, we can actually calculate all of the arrivals and departure times of this case. There's a hard constraint that the departure time needs to be less than due time. So the question here is, what here are shadow variables? Where do we use shadow variables here? Well, the arrival time is a really, really big candidate for the shadow variables. In fact, in the examples, if you go through the stock examples of OptaPlanner, you'll see that the arrival time is the shadow variable. The others, the start time and the departure time, I don't use shadow variables for that personally, because I just use a smart getter. I just say get departure time is equal to start time plus arrival time, and start time is just the max of the ready and the arrival time. So I don't bother writing a variable listener for that. But the arrival time is definitely, if you need to calculate that starting from a particular visit, you need to go through the entire chain of all the visits that come before that and check out and figure out their arrival and departure times. And it's just too costly to do that all the time. So that's a real candidate for the shadow variable. That's what we always use. So here's how it works. We know that from these locations, this is the amount of time to travel between them. We know we start at 6:30 in Brussels. After Brussels, we go to Bonn. After Bonn, we go to Berlin. So we can actually know which time we arrive in Berlin, because we know it takes half an hour to go from the start to Brussels. So it's 7 o'clock, we're in Brussels. It takes 2 hours to get to Bonn. So 9 o'clock, we're in Bonn. It takes 5 hours to get to Berlin. So it's at 2 o'clock in the afternoon, we're in Berlin. If we then add in Amsterdam, and this is where the shadow variable incremental calculation happens, and you'll see this in action right now, is that when we add in Amsterdam, then we know, okay, we're going to be in Amsterdam at 9:30, because after Brussels, we go to Amsterdam. It's 2 hours and a half driving to over there. So 9:30 in Amsterdam, which also means that we will be later in Bonn, because it takes 2.5 hours to get from Amsterdam to Bonn. So we'll only be 12 o'clock in Bonn, which also means we'll be later in Berlin, right? So you have this cascading thing, but it always cascades in one direction, in increasing time, in the future, never in the past. So that's an important thing when you do shadow variables and they evolve in time. Always make sure that your determinations on all of the effects of that increase in time, right? So you go from something that happens earlier in time to something that later in time, and you get this incremental side effects, right? But always in one direction. If you start doing in both directions, that won't work. You'll get infinite loops or catch-22s and kind of things like that, right? But this works quite well. An interesting thing to note is you might say, oh, but what about lunches? What if one of those vehicles, of those technicians that were standing around in the vehicle routing problem needs to have a lunch at 12 o'clock, and we need to actually build in an hour of lunch for that. So what we actually do in that case is, when we detect that one of the visits or one of the transit times between two locations passes the 12 o'clock mark, we add in an extra hour, we pad in an extra hour to give that lunch. In some cases, we might even have jobs that span multiple days. You might even do that for sleeps and so forth, right? But in the simple case, it's for lunch. So what we do is, in our variable listener, in our shadow variable calculation, we basically say, we know that our arrival time is the departure from the previous plus the travel time, right? And we know that our start time is the ready time plus the arrival time. Remember that from the last slide. What we're now doing is that if the travel time while we're traveling, and we're traveling from 11:30 till 12:30, so it contains 12 o'clock, it contains that instance of time, we're going to add 1 hour to the transit time for lunch. So the technician can actually has enough time to drive to the new location, but in between can stop somewhere for an hour to get lunch. If that doesn't happen during the travel time, but during the service time, we actually add it in the service time. So that where he's doing the service, he can actually in the middle of the service stop and go out for lunch for an hour. But these are the tricks to deal with lunches. These are, and notice how the lunches are now deterministic. We don't decide the length of the lunch. We actually know that in advance it's going to be 1 hour and we're going to pad that in at around 12 o'clock. This works well, and so your shadow variable, this is extra logic that ends up in your variable listener. And this can make it complex if you do further logic development. I'm seeing very, very complex logic being added in there. It's all possible. And in some cases, it's a really good idea to do, but be careful. Think twice before using these. We're running a bit out of time, so let me maybe show one more interesting thing around task assignment. For those of you, I'll skip the demo around task assignment, but in task assignment, we're doing the same thing as in the vehicle routing thing a little bit without the changing of times. What we do is we assign certain tasks to certain people based upon their skills. And if we assign the right task to the right person, then there's an affinity and the task takes less long. You can see lunches going on here too, right? Again, when we cross the 12 o'clock mark, we added padding for lunch. Now, one thing we see often in task assignment is a couple of patterns we see, and I'm just going to end with showing a few of these patterns. One of them is the automatic collapse. So for example, here we're assigning 3 tasks to Anne, and we're assigning 3 tasks to Beth. But it turns out we're assigning the change engine oil and the change fuel filter to Beth, and both of them involve opening the engine and closing the engine. This is for a maintenance task problem. And you can basically leave the engine open after changing the engine oil and immediately change the fuel filter without closing it in between. So what we can actually say, if we schedule these 2 tasks behind each other, we get a productivity gain, right? So again, in the shadow variable, in the shadow variable listener, what we can do is we can say, when we see that this task is followed by that task, we're going to eliminate the closing and opening engine cost, because we can just do it in once. We get an automatic collapse there. Similarly, let's say you're delivering pizzas and you need to deliver 2 pizzas, but at 2 different locations, but they're all both coming from the same restaurant. Then you can, the pickup time, right? You can actually collapse that. You can actually say, I'm going to pick up both pizzas, and then I will deliver pizza 1, and then I'll deliver pizza 2. And so you don't have to pay the pickup cost twice, right? So this is an automatic collapse. We have a few more cases, a few more one. So here's I'll just finish with this one. This is the last one I'll show, is the automatic delay until time. Let's say we assign a number of tasks to persons, but the assembling the wardrobe, these are 2 tasks that must start simultaneously. It's because it takes 2 persons to actually assemble that wardrobe, and 1 person can't just start it. It's too dangerous or something, or it's not possible. It's physically not possible. So what we do is, when these tasks are assigned like this, we automatically delay the earliest of those 2 assigned tasks, so they actually start at the same time. So in the planning variable listener, we say that the start time of assembling this wardrobe, even though it can start at 9:20, we see that its buddy task, which starts at 9:40, is starting later. So we're going to automatically delay the start time of this task for Beth for 20 minutes. And of course, that means she will have to wait for 20 minutes. And OptaPlanner, if there's constraints in there which try to reduce the make span, try to do as many tasks as possible, we'll probably end up giving Beth another task in those 20 minutes if it can find one. And of course, you have this with the vehicle routing problem too. We need to cut to that trees in Central Park, for example, and we have the drives in between and so forth. But again, we can see that we will automatically delay the first one to arrive until the second one to arrive. And of course, if we need to be with 3 persons to a job, we just auto delay until the last one. So that's my presentation. I hope it was useful and interesting. If there's questions, I'll happily answer them.
Thank you, Geoffrey. Hey, everyone, you see his Twitter over there? Feel free to follow him to know everything about his life. I'm just kidding.
And, and pay attention to the OptaPlanner documentation. The website is full of information. It's one of the best documented websites and technology that I know. That's amazing job that Geoffrey and team takes care of.
So just so you know, Geoffrey, I already stopped sharing your screen, okay?
Yeah.
So we have a couple of questions in the chat. Do you want to bring the first one, Perchali?
Yes. The first is there a Quarkus task assignment example on a quick start?
No, not yet, but we need one. We definitely need one. We're waiting a little bit on VRP simplification. We're working on something big. It won't be done in the next 2 months, but maybe before the summer, we hope. And once we do, task assignment is going to be one of the examples that will be rewritten and probably completely ported to a Quarkus version. We see a lot of interest in that.
Lovely. Something big. Now you made me feel a little bit curious. So is there a working example or demo for the automatic delay?
No, I've helped multiple customers implement it. We don't have a public demo for it, so that's again something that should actually be in that task assignment Quarkus example. That's a must-have really. That we have a nice example showing it.
Indeed. And how can I assign a custom shadow variable to inverse relations shadow variables?
So what you can do is for a custom shadow variable, you specify the source. You basically say this one might change if any of these variables change. So what you can do is you can say the source is my lesson list there, and the lesson list in itself, which was on the room, might actually be a shadow variable on an inverse relationship variable on the lessons room, right? So you can daisy chain them basically.
We have now a lot of questions coming in. That's amazing. The next question that we have, is it possible to constrain the time for solver running if you are running in Lambda functions environment with timeouts?
Yes, so basically if you go into the termination config, so if you go into the termination, so on the docs on termination, you'll see we support a whole number of terminations. So one of them is simply saying the solver cannot run longer for, let's say, 10 seconds or 30 minutes or 8 hours, whatever the case you submit there. We have many others. You can say after if the score doesn't improve for 3 minutes, stop solving, and so forth and so forth. So yes, Lambda function. If you're playing with Lambda functions, Quarkus built natively. That's minus the native on the school tabling examples. That's what you want to do there, unless you're solving for longer than, I guess, 5 minutes. Then hotspot really is an advantage.
And Geoffrey, people don't only want examples on Quarkus, but they also want the examples on Swing. So please also include the auto delay example in the Swing examples.
This is news to me. This is news to me. Yes, definitely. We will definitely, we're not going to throw away the Swing examples. We're going to make sure that some of them will stay there. We're going to push more for quick starts, really, because of the web. People want to see REST, see the integration with REST and databases or Kafka or whatever the case may be. Right.
Still, it's lovely to get all this feedback of what actually helps people getting started or getting in more advanced projects with OptaPlanner. And simple question, can we have planning variables as a list of objects?
We're working on it. That's VRP simplification. So can we have, for example, a vehicle that has a list of visits? Can we have an employee that has a list of tasks? That would make the user's life so much more easier. And we know that it makes our lives a lot harder, but we're working on it. It's going to be beautiful. Give us the time to do it right.
Awesome. We are having lots of great feedback here, and that makes me feel a lot more excited to keep on bringing deep dive to keep bringing deep dive contents like this one. So thank you, Geoffrey, for all this content. It was a great session.
Yeah, that was amazing, great, and clarified a lot of the magic behind the scene, how things work. It was really, really insightful. Thank you very much for the deep dive content.
Thanks, Alex. Thanks, Karina. It was a pleasure to be here as always.
And just to wrap this up, I'll wrap it up with you here today, Geoffrey. Okay, so stay here with us. Thank you, everyone who was here during the live session, who could ask your questions and make this even more fun and more insightful for everyone. So thank you. Alex, your last words?
No, thank you very much. Follow Geoffrey on Twitter, contact him. Take a look on the website. OptaPlanner is full of great documentation. It's very, very helpful and very good content. And thank you, everyone, for being part of this.
Geoffrey, your last words for our session.
Thank you, Karina, and thank you, Alex. It was a pleasure to be here as always.
Awesome. Thank you a lot. Have a great day, everyone. Bye-bye. See you next week.
Bye. See you next week.
Bye, guys.